the last thing I want to look at in this lesson are graphical representations of limits. And here we have three graphs of functions that are all very similar, but there's slightly different behavior at the x value of a. And I want to look at these three and talk about how in all three of them, the limit as x approaches a of the function does equal L, whatever that y value is, regardless of which of these three situations we end up with. So in the first situation, we can see we've got a graph, and if we want to know the limit of the function as x approaches a, we can look at what's happening to the graph as we get closer and closer to the point with an x value of a. And if you look at what's happening on the left, the height of the point, the y values of the points, are getting larger and larger, and they're getting closer to L. And on the right, they're getting smaller and smaller and closer to L. And we can see here that as x approaches a from either side, the function is basically getting closer and closer to L as far as function values go. So that's what's happening graphically there. Now, it doesn't matter if the function is undefined at the x value a. That's very much in the definition of a limit. We don't care if the function is defined or not at that value. We just care about what's happening nearby. And if you look at the graph, it's getting closer and closer to that point, even though it's an open circle there. And so as x gets closer to a from the left or the right, y is getting closer to L from below or above, and so the limit is still equal to L. And here we have a third situation that's the same as the last, except instead of the function being undefined for a, it is defined, but it's defined as some other random value that's totally unrelated to everything else. And this is totally okay. It does not mess with the limit, because specifically when we're looking at limits, we care about what's happening as x is near a, but we do not care what happens at that exact value. It's totally irrelevant. So whether it's some other random number, or it's totally undefined, or it is defined and it's defined to be the exact value you might expect, does not matter. We always throw that one point out, and we're just looking at the graph near that point to see what's happening to the y values. All right, I want to do one more quick graph of an actual numerical example. All right, here's a quick sketch of the graph of y equals x minus 1 over x squared minus 1. It's not perfect, right? Drawn by hand on my iPad, not perfect, but it is a sketch. And this is a nice smooth curve, but it is undefined when x equals 1. It's also undefined at -1, but we're not going to worry about that because we were looking earlier at the limit of this as x approaches 1. And what the graph actually looks like is a nice curve with an open circle there. There's a hole in the graph because it's not defined at 1. And if we look at this graph, remember we wanted to know the limit as x approaches 1 of this function, x minus 1 over x squared minus 1. And if you look at the graph on the right and the left, because we don't care what happens at 1, we just care what happens near 1, you can see that on the left, it's larger than 0.5, and it's getting closer and closer to 0.5. And on the right, it's less than 0.5, but it's getting closer and closer still, but from the other side. And because in both directions the y values are getting closer and closer to 0.5, we know that the limit itself is equal to 0.5. So that is what's going on graphically for that particular limit. I just wanted to show that so that we can have another viewpoint of what that looks like.